Hello, we are here to do a video walkthrough of practice quiz number 2 for learning target number 3 on exponential functions. Let me focus this here real quick. All right, so we're going to start with golden standard 3.1. Determine whether representation is best modeled by a linear exponential function. In order to think about this, I kind of like going back and starting here first. Linear functions grow by. Well, linear functions always grow by addition. Yes, or subtraction. Just addition by negative numbers. Right? Exponential functions grow by multiplication. Division is just multiplication by a fraction between 0 and 1. So thinking about that really helps us figure out which representations are linear versus exponential. Let's look at this one. How's this one changing? It's going down 0.5, then up 0.5. Well, that's no line that I've ever heard of that goes down and then back up. Is it multiplying by the same amount? No. So that one's just neither, so we're not going to worry about that one. How is B changing? 0.75 to 1.5? That's times 2. Times 2. Times 2. It's times 2 every time. That means B is exponential. All right, so let's look at the third one. I see how is the output changing as the input goes up by 1. 5.5 to 5 is minus 0.5, minus 0.5, minus 0.5. It's subtracting 0.5 every time. That means it is linear. Let's look at our graphs. Linear, we know that's a straight line. D is our linear graph. It's a straight line. Exponential is that curve that kind of goes, whoosh. It doesn't go up and down. It always continues moving in the same direction. Therefore, the exponential graph is F. Let's think about our linear equation. Y equals mx plus b. We have a slope and a y-intercept. No exponents. That would be H. Which equation then? G or I is exponential. They both have exponents, but exponential graphs are defined by the variable, the input, being the actual exponent, a times b to the x power. So G is the exponential equation. And lastly, 12-ounce jar of peanut butter, and you eat 10% of the remaining amount. If you eat 10%, that first day you're going to eat 1.2 ounces. You're left with 10.8. What's 10% of that? It's 1.08 ounces. The amount you're eating is going down and down and down every time. Therefore, it is exponential. All right. Sorry, it's going down by different amounts. It's multiplying by 0.9 every time. Whereas for K, you start with a 12-ounce jar of peanut butter. You eat 2 ounces a day. That means you're eating 2. Then you've eaten 10 ounces, then 8 ounces, then 6 ounces, then 4 ounces. It's a constant growth or decrease by subtraction. All right. Let's go on to golden standard 3.2, translate between exponential equations and graphs. So sketch a graph from the equation y equals 2 times 1.5 to the x. I always like to start with our initial value. Our initial value right there is a, the a value. 2 means our y-intercept is at 0, 2. So we're going to plot that first. I know the graph's a little bit faint, so we're going to put it right there. Then where do we go next? We're going to take that 2 and we're going to multiply it times 1.5. 2 times 1.5 is 3. So 1, 3. Okay. Next, multiply 3 times 1.5. So after that, we take 3 and we multiply 3 by 1.5 to get 4.5. So 2, 4.5, which is right around there. And then multiply that, 3, 6.75, which is right around there. I know it's hard to see on there. The graph's a little bit faint. It'll be copied better next time. Don't forget also, it doesn't start here. It keeps going back into the negative x values. 2 divided by 1.5 gets us down to about 1.333, and then we're about a little under 1. So our graph looks like this, exponential growth, because our multiplier is greater than 1. Now, be sure to graph any asymptotes. What that means is there is an asymptote right down here at y equals 0. So all we want to do there is mark it with that dashed line and record it as y equals 0, showing there is an asymptote. Okay, for the second part, find the equation for the graph. I'm going to use the systems method here. So I'm going to write my later point, which is my output is 0.5, equals my initial value times my multiplier to the 5th power, my input. Output, y is 0.5, input 5 is the x. My other point, the output is 32. It's my initial value as my multiplier to the negative 1st power. Now, what do I do with those two terms? I'm going to divide them. Now 0.5 divided by 32 comes out to a small decimal, 0.015625. And I want to keep it written out to get a precise answer after this, because otherwise the root's not going to work cleanly. B to the fifth divided by b to the negative first. When we divide exponents, what do? We subtract them. 5 minus negative 1 is b to the sixth. And I forgot to mention, the a values cancel out. The same number divided by itself is just 1. So 0.15625 equals b to the sixth. Therefore, the sixth root of 0.015625 is going to equal whatever the sixth root of b to the sixth is. Turns out the sixth root of this decimal is 0.5 equals b. So my multiplier is 0.5. Each time this graph is going down by 0.5. You might be able to see that from the graph itself too if you see 32 down to 16, to 8, to 4, and so forth. All right. Now how do we solve for the a value? Well, we can see it here on the graph. We can see right here the a value is at 0, positive 16, excuse me. What would we do if we couldn't see it exactly? We'd have to solve for it. To do that, we could do something like 32 equals a times our multiplier to the negative first power. So 32 equals a times 2. Divide both sides by 2 to find that 16 equals a, our initial value, as we see on the graph. Therefore, what is our equation? Y equals 16 times 0.5 to the x power. All right, those are our two golden standards. Let's flip to the back side. All right, so first one here for 3.3, translating between equations and context, knowing how to rewrite these. So the first one says 80,000 fish in a lake are exposed to pollution and the population declines by 22%. Now, I like to underline the important parts here. 80,000 is where I'm starting with. I'm starting with the initial value of 80,000 fish. That's going to be my a value. Now, what's my multiplier here? It's going to be based on this decline right here. So how does this work? I start at 100, and if it declines, that means I'm taking away 22%, meaning 78% remain every month. I can't use 78% as a multiplier. When I use a multiplier, I have to use a decimal. 78% converts to 0.78. So therefore, my multiplier is 0.78 to the x power. For the second one, I've got two parts here. I have my initial value right here, which is 2. So that means our context needs to reference that it starts at 2. And then what happens to it? It multiplies by 5. It quintuples every time. So, or it increases 500%. 400%, sorry. Increases 400%, right? Because it's 100 times plus 4, we'll get 400%. So it either quintuples or it increases 400%. Your choice. As long as your context references that it starts at 2 and then multiplies by 5 or increases 400%, great, you're good. Why can't it be increases 500%? Because then 100 plus 500 would be 600, meaning our multiplier would be 6. It's tricky right there. So as long as your example fits those two, you're good. One example I might write is something like, there are 2 bacteria at midnight, and every hour the population multiplies by 5. That works. All right, let's go on to 3.4, compound interest. What I'm going to suggest you do here is to write the initial formula out, okay? So for compound interest, your output, y, amount, whatever you want to do, your output is your initial amount, what we call the principal, 1 plus whatever the rate is, divided by how often it's compounded, to the power of how many times it's compounded, times how many, the time usually years of how long it's invested. Okay. So LaMelo received a signing bonus of $10,000 when he was drafted into the NBA. He wanted to follow his dad's advice and invest his full bonus rather than spend it all right away. Smart idea. And ended up choosing between two options. He could invest in an index fund projected to earn 4.5% compounded annually. If he didn't spend any of his signing bonus and invested all of it away for the duration of his projected 15-year career, how much will he have when he retires? So, what are we doing here? We're starting with $10,000, his full signing bonus. 1 plus. Now, we're only compounding it once a year. So that means we're just taking this 4.5% and turning that into our multiplier. So 100 plus 4.5% gives us 104.5%, which converts to a multiplier of 1.045. So we can see that here, 0.045. Now, how many years is it going to be invested? 15. So that's 10,000 times 1.045 to the 15th power, which works out to be $19,352.82. Now, let's look at his other option. LaMelo has some friends who want to start a business, and they are promising him a 3% return compounded quarterly until he retires. So if he retires in 15 years, which option earns him more? The index fund, right up here, or investing in his friend's business? Justify your answer algebraically. So we already know how much the index fund will return. Let's find out about the investment in his friend's business. So we're starting with the same $10,000. Now we're going to grow here. We're going to grow by how much? 3%, which works out to be a multiplier of 0.03, divided by 4. Why 4? Because quarterly is 4 times per year. It's compounded 4 times per year. And then we're going to, our exponent is going to be 4 times a year times 15 years. Basically, we're breaking this 3% rate up into 4 compounding periods, which means we have to make sure we actually account for how many periods are being compounded. 4 a year times 15 years. So let's simplify this down. That's 10,000 times 1.0075 to the 60th power. That works out to be 10,000 times 1.5657, which works out to be about $15,656.81. So what's the better option? Clearly, the index fund is the better option. How much more will he earn? Well, he earns $19,352.82. At the index fund, $15,656.81 with his friends right here, meaning that at the end of the day, he will earn $3,696.01 more with the index fund. All right. Hope that was helpful. Good luck with your mastery quiz.